The topic of my talk is new standard for LRFD design of pultruded structures. I will be talking about the background, the LRFD design philosophy, and material requirements, design of members, design of connections, seismic design, and end it with the conclusions that we can derive from this. The ASCE standard, which is identified at ASCE SEI 74, is a standard for LRFD design of pultruded FRP structures, and it's accredited by the American National Standards Institute. The entire process is reviewed and accredited. This accreditation means that the process met the requirements of openness, balance, consensus, and due process. There are challenges in the design of pultruded FRP composites due to anisotropic or orthotropic nature of the material that makes the job of design difficult but allows innovation. Creep and creep rupture of material is a characteristic of the pultruded FRP composites, which is not in many of the isotropic homogeneous materials such as steel, or for that matter, concrete. When it comes to durability, although pultruded FRP are not susceptible to corrosion in the way that steel is experiencing. However, it does lose strength to some extent and modulus with exposure to different environments. And this is essentially taken into account by looking at the retained properties. The goal of the design is to use this material in new buildings, in new bridges and other structures constructed with pultruded FRP, assist in design of connection, as well as construction of the prefabricated building components, industrial buildings, especially those that are subjected to very harsh corrosive environments such as seawater, and structures that can withstand earthquake because this material has extremely high strength to weight ratio. The content of this standard includes 9 mandatory chapters with mandatory requirements and 9 chapters of commentary, which are not mandatory, plus 2 chapters that one is on glossary and the other one is on symbols. The chapters cover general provisions, design requirements, as well as design of members for tension, compression, flexure, and shear, and combinations of forces and moments and torsion that are applied to individual members, as well as design of plates and build-up members and bolted connections. There is a chapter also devoted to seismic design in addition to glossary and symbols chapter. What is the design philosophy of this standard? The goal was to develop a standard that, following this standard, would result in structures that provide the necessary strength, they have durability, and they have reliability in par with other materials of construction, and they account for time effects from creep and creep rupture of material under sustained loading. Let's look at it in an equation. If R sub U is the required strength when the structure is subjected to factored load combinations, then this required strength should be less than or equal to the capacity. But how do we define the capacity? The capacity is the product of three terms. One is time effect factor that accounts for creep and creep rupture, resistance factor that accounts for variability of resistance and bias, and nominal strength in the end use condition. If we consider what is the meaning of the strength in the end use condition, we can express it as a reference strength, R sub naught, which is the strength of the new material as tested in the laboratory, and a coefficient, which is a knockdown factor, is material adjustment factor, that accounts for the exposure environment that the structure is subjected to during its service life. Let's look at each component. Loads, load factors, and load combinations, we talked about them. Where do they come from? These are essentially the same regardless of what is the material of construction, and they are specified in ASCE 7, which is the document entitled Minimum Design Loads and Associated Criteria for Buildings and Other Structures. Many different load combinations are given, and there are load factors that are associated with each load and each load combination. For example, as an example, dead load and live load on a building are treated essentially with load factors that you see 1.2 for dead load and 1.6 for live load. But these factors and these loads are the same regardless of what is the material of construction. Strength. Strength is defined with reference strength, which is new material, as tested in the laboratory following ASTM standards. However, what do we do with the test results once we obtain? Here is what we rely on, an ASTM standard that has been published, that we look at the reference strength as the 5th percentile value of the test results with 80% confidence. Now, confidence has to do with size of the sample that you are testing. And once you have the reference strength, the nominal strength is the strength in the end-use condition. As I said before, it's the product of material adjustment factor that accounts for durability and the reference strength. How do we get the material adjustment factor, which is the basis of durability? We expose the material to different environments for a long period of time, between 1,000 and 10,000 hours. And then after exposure, we measure the properties such as strength or modulus, and take the mean of that and compare it with the mean of the new material that has not been exposed. And then extrapolate the results to the expected life of the structure. And this way we establish the factor C, that from which the nominal strength is calculated using the reference strength. The standard provides for two exposures, one being moisture and the other temperature, values that are, as you see, vary for strength and modulus, and also vary with the type of resin. And also in the case of temperature, it also varies with the level of temperature. And these values have to, if you have both moisture and temperature, they have to be multiplied together in order to establish the material adjustment factor for a product that is exposed to both moisture and temperature. Resistance factor is another factor that we talked about, and it comes into the capacity. The resistance factor accounts for bias and variability of resistance. What is bias? I present to you the compressive strength of a pultruded square tubes, and you will see that using the best equation that money can buy, still the test results coalesce around 80% of the predicted value. Therefore, there is a bias that of 0.8 that has to be accounted for. And what about variability? Variability goes back to probability of failure or probability of survival. How many standard deviation do we have to go below the mean in order to have the reliability or probability of failure which we desire the structure to have? And that number is called reliability index. Two structures made of completely different materials, so long as they have the same reliability index, they have the same performance and the same reliability. And this is the basis why we can claim that structures that are designed in accordance with this standard from standpoint of reliability are in par with other materials of construction, because we selected the reliability index very similar to those that are used in other materials of construction. It's variable. For example, general instability is between 3 and 3.5. And as you get to local instability that you don't want it to occur at the same time as general instability, you put it further away. It's 3.5 to 4 until something that you don't want it to fail at all is connection that you assign to it reliability index, which is higher. Time effect factor is done essentially by subjecting the member or component or structure to a load which is less than its strength and measuring time to failure. Then we extrapolate the results to the design life of the structure. And based on that, we get a factor, a knockdown factor on strength. For example, for permanent load using Pultruded FRP, you have a factor of 0.4 reduction due to permanent load effect. However, since load combinations are combinations of different loads, some of them may be instantaneous like wind and earthquake, and some of them may be permanent like dead load, and some may be in between like live load. These combinations have much higher time effect factor, as you see in this table, and which is an extraction from the standard. Design of the members. There are chapters that are devoted to design of members in tension, compression, flexure, shear, axial force and bending, axial force bending and torsion, and flat plates that we will not go through all of them, but I'll take one as an example, and that's compression members. In the case of compression members, we look at different modes of failure. For example, rupture of the member in compression, general buckling of the member, and here the issue of imperfection comes into play, and local buckling of the flanges and webs and slenderness ratio. All of these are sensitive subjects that influences the strength and are well discussed in this chapter. And each one of these failure modes are associated with it equations that manifest the behavior of a member, and there are different shapes and different members, so there you can imagine that this can be quite an extensive chapter. Design of connection is an important chapter. We look at single bolt and what are the failure modes of a single bolt, and then we generate the capacity by looking at all possible modes and selecting the one that governs or with least amount of capacity. And then if there are rows of bolts or rows of or multiple bolts in a single row or gusset plates that may be completely different, we get interesting results. For example, here I'm showing on the top, I'm showing essentially different modes of failure of a single bolt. The bolt can fail in tension or shear. It can, the single bolt connection can fail in pull-out tension, pin bearing, net tension, shear out, and cleavage and net tension splitting, which are depicted in the figure that I'm showing on the right-hand side, as well as if there are multiple bolts, you get block shear, which you have to prescribe what is the failure perimeter or what is the failure mode. And then based on that, you can calculate the strength associated with it. Seismic design. It was necessary to develop a chapter on seismic design. One reason was for completeness, and the second one is really the product has a very fantastic high strength to weight ratio, and it's ideal for application to excitations from ground motion. The earthquake load is defined in the same way as for any other structure in accordance with the requirements of ASCE 7. The standard also meets general structural integrity provisions of ASCE 7 when you design Pultruded in accordance with the requirements of this chapter. To resist lateral seismic loads, Pultruded FRPs are required to have braces at this time. Maybe in future, with enough testing, other connections may become acceptable, but at this time, for the confidence that we want the designers to have, we require that any lateral resistance is provided by bracing. We are providing initial seismic design parameters, but these parameters are subject to change in future as testing progresses. And it should, these seismic parameters have to go into building codes and other standards. In conclusion, I can say that this new standard will enable the structural engineers and architects to create and safely design new buildings, new bridges, prefabricated components, and structural system, and artworks that are easy to construct and have high strength and lightweight and can resist adverse environments, and they are not subject to corrosion that other structural materials are. Anyway, that terminates my talk, and later on I will be responding to any question that you may have.